Welcome to Sysadmin. In today's video, we are going to explore principles of serial transmission and network impairments. It seems so simple, right? You click a mouse, a web page just appears. But that one simple action hides this brutal, chaotic journey that your data just took. For a sysadmin, really understanding this physical layer, the actual wire, is everything. Because when things inevitably go wrong, knowing how a signal survives, or dies, is the only thing standing between you and some pretty catastrophic downtime. So this isn't just theory, it's the absolute foundation of a stable enterprise network.
Okay, let's dive right in. At its most fundamental level, all of our complex data, every single email, every video you stream, every database query, it all has to be deconstructed. It gets serialized into this simple, single-file line of ones and zeros, all ready for its journey across a physical medium. That's the core task. But how do you bring order to that chaos so the computer on the other end can actually piece it all back together?
While this slide shows the two competing philosophies for managing this flow of bits, you can think of asynchronous transmission as sort of a relaxed conversation. Data gets sent in casual, irregular bursts. On the flip side, you've got synchronous transmission. This is more like a disciplined military drill, where these huge blocks of data march in perfect lockstep. Each approach has its purpose, and choosing the right one is a critical design decision with massive implications for cost, speed, and reliability.
So let's get into the mechanics of it. How do these two methods solve that fundamental problem of communication? Letting the receiver know without a doubt when a message begins and when it ends. This is really the heart of data link control.
Let's start with asynchronous. The best analogy I can give you is sending a series of individual postcards. Each character of data, like the letter A from your keyboard, is its own self-contained package. It really doesn't matter if there are long, unpredictable gaps between them, because each postcard has its own address and postage, its own special signals to say, hey, I'm starting, and okay, I'm done now.
Let's break down how this actually works on the wire. As you can see here, the line is normally just sitting there, idle, at a high voltage, which we call a state of 1. Then a start bit suddenly drops the voltage. That acts like a starting pistol, alerting the receiver that, hey, data is coming. Then the actual bits for the character are sent, followed by 1 or 2 stop bits, which raise the voltage right back up to idle, signaling the end. This entire frame, start, data, stop, it's all dedicated to just a single character.
So the crucial thing to understand here is the trade-off. It's super simple and cheap to implement, which is why it's perfect for devices like your keyboard or maybe some sensors that send data in small, irregular bursts. But that simplicity, it's costly in other ways. At least 20% of your transmission is just overhead. Those start and stop bits aren't your data. They're just the packaging. And for an enterprise, that is a ton of wasted bandwidth. Even worse, a single glitch that corrupts that start bit makes the entire character completely unreadable.
Now, let's look at the other philosophy. If asynchronous sends postcards, then synchronous transmission, well, it uses a massive shipping container. You don't send individual characters. Instead, you bundle thousands of them into a single large block and send it all at once, governed by a very precise shared clock signal.
So how is this huge block organized? Well, instead of start and stop bits for every single character, there's a unique flag pattern that marks the beginning and the end of the entire block. In between, you've got your data payload. And crucially, it includes some really sophisticated error checking, like a cyclic redundancy check. You can think of that as a complex mathematical signature to verify the integrity of the whole block. This is a system built for bulk transfer. The benefit here is just astounding efficiency. The overhead is minimal, which makes it the only choice for high-speed, high-volume data transfers like server-to-server backups or your core network traffic. The downside? It's a lot more complex and expensive. And the stakes are way higher. An error doesn't just corrupt one character, it can force the retransmission of the entire massive block, causing a really noticeable delay. So, now we have our 2 strategies for organizing data, but the real challenge is actually just beginning.
All right, now that we know how we want to send the data, we have to face the brutal reality of where it's going. The physical medium, that copper cable, the fiber optic strand, it's not some perfect, sterile conduit. No, it's a hostile environment, and it is actively working to corrupt and destroy our perfectly organized signal.
This is a truth every single sysadmin lives by. If our world were perfect, that beautiful square wave of a digital signal we send would be exactly what's received on the other end. But it never is.
As that fragile electrical signal travels, it's under constant attack from three major enemies that we are always fighting.
First up is the energy thief, attenuation. It's simple physics, really. As your signal travels down a wire, its energy just dissipates. It gets weaker and weaker and weaker. So we use amplifiers or repeaters to boost it back up. But here's the catch. An amplifier also boosts any noise the signal has picked up along the way. It can't tell the difference between the good signal and the bad. This is exactly why an Ethernet cable has a hard length limit of 100 meters. The second enemy is delay distortion, and this one is much more insidious. Think of it like a race where the runners don't stay in their lanes. Different frequency components of your signal actually travel at slightly different speeds through the wire. This causes the signal to spread out, basically smearing the sharp edges of your ones and zeros. It's a complete catastrophe for digital data, where timing is everything. Bits can literally bleed into one another, creating total gibberish at the receiving end. And finally, we have the most unpredictable enemy, noise. This is just random, unwanted energy that invades your signal from external sources. It's the static on the line, the signal scrambler that can flip a 1 into a 0 or a 0 into a 1, silently corrupting your data in ways that can be incredibly difficult to track down.
And this noise, it comes from everywhere. There's thermal noise, which is just the unavoidable background hiss from the random motion of electrons. That's the price of doing business with physics. Then there's crosstalk, where the signal from one wire in a bundle bleeds into an adjacent one. But the one that really keeps sysadmins up at night is impulse noise. Sudden, massive spikes from motors, power lines, or even a lightning strike. These are the assassins that can just wipe out entire blocks of data in an instant.
So I know this all might seem a little abstract, but for a system administrator, this is the battlefield. This is what's happening in the trenches every single day. Users don't report delay distortion. They report that the internet is down or my files are corrupted. And it's our job to be the detective to translate that symptom back to its physical cause.
Let's look at this with a diagnostic mindset. A user reports intermittent connection drops at 2 p.m. every day. The problem? A huge piece of machinery in the warehouse next door powers on, generating impulse noise that corrupts the data on a poorly shielded cable. Or a whole department complains of sluggish performance. Your analysis? Someone ran a 150-meter Ethernet cable, and severe attenuation is causing massive packet loss. Critical database files are getting corrupted during transfer. The solution? Replacing an old, degraded cable run that was causing severe delay distortion. See? This is real-world troubleshooting.
Whew! We've covered a lot of ground, from organizing bits all the way to the physical forces that are trying to corrupt them. So let's just distill this all down to the 3 key takeaways you should remember.
First, all complex data is serialized, and we use disciplined strategies like synchronous and asynchronous transmission to bring some order to that flow. Second, the wire is a hostile environment. Our signal is in a constant battle against attenuation, distortion, and noise. And third, and this is the most important one, real-world troubleshooting always starts at layer 1. Network stability is built on a solid understanding of these physical principles.
So remember this, that effortless flow of information that we see across our networks isn't a given. It's a complete engineering marvel. Every single packet, every clear message that arrives intact is a hard-won victory against the fundamental chaos of the physical world.
So, a final thought for you. We've identified the enemies, attenuation, distortion, and noise. The critical question now is, how do we design our systems to fight back and actually win that battle? That's where things like error-correcting codes, signal modulation, and smart protocol design come into play.
If you found this helpful, subscribe to Sysadmin Academy and continue building your IT expertise.